speaker. And so here we're going to be hearing about static analysis of infrastructure as code by Barak Schoster, who is the CTO and VP of engineering at Bridgecrew. And I will say, this is a talk I've very much been looking forward to, because I think anybody that works in cloud, certainly that works in DevOps and focuses on automation and trying to better automate infrastructure within the cloud environments that we're in, have struggled with this. This has been an area that I know security professionals have really looked for solutions to really, help us find security parameters, misconfigurations, pretty much anything we can come up with. So with that, Barak, take it away.
All right, thank you, Brian. Hi everybody, nice to meet you all. Let's see that I can control the screen for a sec. Alrighty, so welcome to a special session about cloud security infrastructure and how we can identify misconfigs using static analysis of infrastructure code. So a little bit about myself. My name is Barak Schoster, co-founder at CDO, a cloud security startup called Bridgecrew. As part of my work at this startup, I help teams to secure their cloud infrastructure. And I also contribute to various open source projects like Prowler of Tony Blix that was presented previously here at SANS Cloud Security Summit, and various open source tools that we provide for infrastructure security around Terraform, CloudFormation, and Kubernetes, and also projects around GCP security. If any of those interest you, please feel free to reach out to Twitter. It's Barak Schoster Common Case. All of those are open source and under the Apache tool license. So let's talk about what we're going to talk about today. We're going to talk about what is a cloud misconfig and what is the state of different cloud misconfigurations at the open source repositories and registries. We'll talk about where can we find those misconfigurations and how can we utilize runtime analysis tools to identify those, and how can we use static analysis tools to prevent those from happening again, and how do we choose between the two approaches. So let's start by discussing about what is a cloud misconfig. The famous ones are open S3 buckets that someone left in the wild, open to the entire world. And what usually happens is that an attacker might identify this S3 bucket and just download this data. Another one can be a non-least privilege row, and there can also be a combination of application security, non-least privilege environment, and a misconfig, as was mentioned in the different newsletters about the cloud breach of Capital One. Other ones that are also can be found in the different configuration of different infrastructure in the cloud providers are unencrypted databases, insecure protocols like lack of using TLS, and vulnerable microservices or vulnerable containers in the cloud. All of those can be identified as a cloud misconfig. So where does those misconfigurations come from? How do they arrive into our own organization? So let's think about how we consume those templates today. So if we want to build a new application, we'll probably look at Stack Overflow. Hey, how do I stand up a new database, a new RDS, PostgreSQL, or MySQL? I will probably reach out into an AWS blog or Google Cloud related blog, and from there to the Terraform registry or into an open source solution on GitHub that has a pre-made cookbook or a template that has all of the resources that requires to be provisioned to stand up a new database. It is good to use those because it lets me as an engineer focus only on the business logic, and I can already use a pre-made template that somebody already tested with the networking configuration, encryption, access, IAM policies already defined in what Terraform calls, for example, a module. These modules can also be built within your organization in your internal GitHub repository or private Terraform registry. but those are usually built by platform engineers or infrastructure engineers that does not always have security in their mindset. But even if they do, they can do mistakes and they can forget one configuration that can turn things in the opposite way that we wanted them to be. So what I did is I used the tool that I've developed and I've sampled 1,700 GitHub repositories that has infrastructure modules, Terraform modules within them. And what I found is that 47% of those modules were misconfigured. And those are the different misconfigurations that we've talked about before, like having a public resource or unencrypted resource in the cloud. And what was more troubling is that from those 47% of misconfigured modules, those modules had, by the GitHub statistics, 8 million downloads. That's a lot of misconfigured resources provisioned in the public clouds. Well, those might have been fixed manually. It is still a lot of work to fix those. And if no one fixed those misconfigurations, those are a lot of easily breached resources on AWS or Google Cloud. What I then tried to understand is how those modules look over time. So I've sampled the usage and growth of modules over the registry across from 2017 till 2020 this month. And what we can see that is good is that we have more and more open source contributions. We have more and more new modules, which is great because more boilerplate code that is being made by others is less work for me as an engineer. The downside of it is as more modules are created in the open source community, there is more misconfigs that are available in the open source community. So if someone will use one of the public, the most common EC2 instances Terraform module, they will probably discover that it's not encrypted by default. The EBS snapshot is not encrypted by default. And what's more interesting is that during COVID, when everybody were stuck at home, they had more time probably to write more code and to create more open source modules, and with it, more misconfigured modules. So let's pause for a sec. As an engineer, I probably want to use a pre-made code that was already tested and contributed and is maintained by the community. And this is super cool to use those. And what I'm asking myself is how can I use that responsibly, knowing that the infrastructure that I bring from the outside world, from the pre-made GitHub repository, is fine to use on my production environment. So we will start with how do I find those bad configs among those infrastructure modules? The first approach to do that is Prowler, which is an awesome tool that was displayed at the Cloud Security Summit a few years back. It's very simple to use. It's also Apache 2 licensed. It is basically doing API polling and describe calls to the different AWS resources. And from there, it creates some kind of a database that tells you what is a best practice and what is a drift from a best practice across different benchmarks, like the CIS benchmark, GDPR, and PCI. You can run Prowler on a scheduled basis using a CloudWatch trigger. So a common architecture would look like, hey, I have this production account with databases, IAM policies, S3 buckets, and some compute instances provisioned. What AWS will recommend you is to create a security account that is connected to your source account with cross-account role and has various security tools to monitor every activity across the different environments. So if you have a duplication of the source account as dev account, QA account, production account, or various teams or application parts, you can have one centralized security account to monitor all of those. Within that security account, you'll need to deploy a CloudWatch trigger that will run Prowler inside a container, an ACS cluster, for example. will describe the status of all of the different resources and will tell you, hey, you are in a good state or a bad state. And by that, we'll trigger a remediation lambda that can, for example, encrypt an S3 bucket that was provisioned without encryption. Let's see how does that look like from a demo environment.
You should be good.
All right. So what I have here is a pre-provisioned environment that I've created before this session. What I'm going to run is Prowler on my demo profile, and I'm going to call a specific check called extra 73 that will look for public S3 buckets. And it found one, which is usually a bad thing, but on a demo, it's good to see. So I have here a data bucket that is public. So I'm running currently from my own laptop and terminal, but what I can do on ECS cluster is to run that continuously, like every hour or every day, and get a continuous monitoring and state of the current environment. Let's try another one. What I'm going to try to find now is plain text access keys, meaning access keys that are not encrypted and can be fetched using either cross-account roles or someone that has a security auditor role into my environment or read-only role into my environment. So we found two different EC2 instances having plain text secrets within them. Let's try to see what those secrets look like. What I'm going to run now is a command to decode the secrets that are in base 64. And what I can see here is access key and secret key that can be used by an attacker. So how does those access keys and secret keys are usually used? An attacker can use those to provision a new resource in my AWS environment. And for example, use that resource to install a crypto miner and just mine using the resources that I pay new money. So what I will get from that attack will probably be a huge AWS bill. Let's go back to the deck and try to understand where does that leave us. So what we had now is an environment that is continuously monitored, and I can get alerts and remediation based on those. But Prowler is a single tool that will remediate the actions of all of the different engineers that I have. And let's say that I have 100 engineers in my team that are doing infrastructure changes. Prowler will act after the fact because it's running on the production environment on a scheduled basis. And it will always find new mistakes of engineers that are doing those. And the issue with it, since it's monitoring the resources and not the actions that the engineers themselves have done, is that it does not know who have done this mistake. I cannot, using Prowler, I cannot tell to Mike, which is an engineer in my team, hey, I saw you provisioned a new S3 bucket without encryption. Please don't do that again. Or I can, but it will be like a ton of Jira tickets and a ton of talks. This is why we decided to open source Checkov, a tool that can catch the changes while an engineer is writing the infrastructure code that provisioned those resources. So Checkov is a static analysis tool for Terraform, Kubernetes, and CloudFormation. It's written in Python. It has more than 100 built-in checks, and it basically can run like a test suite as part of your CI/CD pipeline. So just like you're running application tests, you can run now infrastructure security tests. And every time an engineer will do a change request or a pull request in GitHub, the engineer will have yet another test executing. And this test is called Checkov. Checkov will run a set of 100 infrastructure security tests and will scan your Terraform, CloudFormation, and Kubernetes. If Checkov has found a mistake, like plain text access keys, it will fail your build and will ask the engineer that have done that to fix that. And if the engineer have fixed that on a new commit, a new change request is being executed. Checkov can be executed again as part of the Jenkins or Circuit CI or GitHub action. And probably it will approve since the change was fixed. And then a deployment trigger can be executed. And either Terraform, CloudFormation, Kubernetes, or all of those can provision a new release of your security account, of your cloud infrastructure. So to demonstrate the next phase of how do I find those vulnerable resources on my endpoint before provisioning that environment, I've created another project called TerraGoat, which is a vulnerable by design infrastructure as code Terraform template. It has public S3 buckets and some access keys that we saw that Prowler caught. Let's see how does that look like. All right, so what I have here is a Git clone of the TerraGoat project. And within that project, I have a Terraform directory that has EC2 Terraform file, for example. But I can see that in this code, I have those access keys defined in plain text, which are bad. And I also have here an unencrypted EBS volume and a various other bad things that was defined on purpose. But this could have been your own code in your infrastructure production environment, and someone might have just forgot those access keys or forgot to turn on encryption. So what I can do to catch those, first I can pip install Checkov. It will probably execute for a few seconds. And then what I can do is run Checkov minus directory. And I will try to analyze the Terraform directory. And I want to show only the issues in that environment. So let's see what it caught. So I have a bunch of issues on that environment. Among them, I can see the S3 bucket that is not encrypted, S3 bucket without logging enabled, and also the unencrypted EBS volume and the plain text access keys. So what Checkov will give you is a full report of each infrastructure as code framework, the amount of failed checks and passing checks, and you can also choose to skip some of those just as you would skip a unit test. And it will give you a full report, either at colorful CLI, JSON, or a CSV. So that's great. I could catch those issues while I'm developing those. So let's go back to the deck and see how does that look like when I want to distribute it. So what I've done is to run static analysis tool using a CLI on my endpoint on my laptop before those resources were provisioned. But the question is how can I prevent from commits to arrive to the GitHub at all before having a pull request? Let's see how does that look like. So what I'm going to show now is a configuration of a pre-commit hook that will prevent me from running commits containing changes of my infrastructure and templates. So let's run a git status and try to understand what is the change. So there was a modification to the EC2 Terraform file. What I will try to do now is I will try to commit that change, and I will see if I succeed. So on each commit, I'm executing Checkov, and what happened now is that the commit got blocked. The change could not arrive even to GitHub itself. meaning if I deploy a pre-commit hook on each and every endpoint, every engineer will not be able to push an unvetted code of infrastructure without Checkov allowing that to do so. So we can deploy Checkov on each and every endpoint on my organization, but really that's a lot of work. The best way to do it is to embed it into your CI/CD pipeline. So Checkov has a great GitHub action, but also integrations with Bitbucket pipelines, GitLab, CircleCI, and other CI tools. It's very easy to deploy. It's a simple configuration file. And what the GitHub action will give you is during the pull request, it will just show you within the line of the change, the issue that was found, like the plain text access keys or the unencrypted EBS. And it will create a full report inside your pull request that the engineer had created without the need to deploy Checkov on each and every endpoint. So Checkov is publicly available. It already has more than 300,000 downloads, and it became quite popular. And it is also being executed at various very large organizations. So feel free to use it, and also we will accept any contribution that you'd like to do into that repository. So let's conclude the two approaches again. We have Prowler that does runtime analysis of the AWS configuration, and we have Checkov or other tools like OPA or ConfTest that can execute static configuration analysis of the infrastructure files. So let's run again on the runtime tools. The AWS config analysis tools is centralized in the security team, and it's not tracking against each and every activity of a developer in my organization. It's probably part of the production monitoring, which is good because I know only of the true state of the environment. It is scalable across multiple accounts using ECS clusters and cross-account roles. It takes several minutes to identify since it's running on a scheduled basis, and it addresses the compliance and security and SRE, which are not the developers. Static config analysis is distributed by design because it's running as part of the CI/CD pipeline on each and every change. It is scalable across multiple GitHub repositories. The downside of it is that it is not aware of the production state. So even if someone did a change manually on the AWS console, Checkov would not be, or any static analysis tool would not be aware of the state of your production environment. It is only familiar with the state of the code. So if you had a downtime and one of the SREs have decided to modify a bucket configuration, Checkov wouldn't know if it was done using the AWS console or an API. Prowler will identify that. It takes seconds to identify because it really runs really fast on each commit, and it addresses the developers, which are usually more than us, the security practitioner in the organization. So what should I do? What should I choose? Should I choose runtime analysis tool or static analysis tool to monitor my environment? And the answer is that you should do both. Let's take a look on how an architecture of both Checkov and Prowler would look like. So you will have Checkov as part of your CI/CD pipeline, like GitHub Action, monitoring each and every commit and every infrastructure change. And on the other hand, you will have Prowler, monitoring your production environment, detecting any activity that was made manually on the AWS account or any activity that cannot be identified using a static check. All right. If you have any questions, I would love to answer them.
Yeah, we have a couple of questions. That was an awesome session. I did not even, it was really some of my favorite sessions because I didn't even realize this was a problem. And you walked us through that half the modules are misconfigured and 8 million people, there's 8 million downloads for it. But the real bad news is it's getting worse because people are continuing to add more misconfigured modules every day. So Eric and Fred basically asked the same question, which is this extensible? Do you have to, like, how do you add your own rules to this? Is there, like, you have to change code? Like, how would somebody write their own checks against this?
All right. So Checkov is written in Python, and you can load an external directory with additional checks to the 100 existing ones. So it has a very basic pip install, and you can use it as an SDK, and you can load more and more checks into it. And there is a simple command called Checkov -- extra checks, which is, and you give it a directory of the extra checks, and it loads it as a plugin. I will send a link on the Slack channel as a reference.
Yeah, I think that's great. I think people have a lot of ideas that they want to kind of change into and do their own kind of checks on. Another question was, what is the output format that's supported for this, like from a reporting perspective?
So it has JUnit XML, which is the basic output format for Jenkins reporting, for example, and also CLI, JSON, and Markdown.
JSON, gotcha. Okay.